so the first thing that we need to talk about in 1-3 is the distance formula. So do you recall, if you have 2 points in the coordinate plane, do you remember what the distance formula is? Usually people don't, because it looks like it's got so many parts to it, but it's really not so bad. So here it is. Let me zoom in so we can copy it down correctly. You have a big old square root, and then underneath that square root, in the first set of parentheses, you're going to subtract the x's from each other. So usually we do x2 minus x1, but if you forget and switch them, it actually doesn't matter, because you're going to subtract them and then you square that answer. So since I'm squaring it, it doesn't matter if I do 5 minus 3 or 3 minus 5, because once I square that number, I get the same thing anyway, okay? But the formula is 2 minus 1, you're going to square that. And then you're going to add to that, same thing with the y's. So you want to do y2 minus y1, close it, square it. Okay, is that ringing a bell? Now that you see it, you've seen that at some point before. So there's your distance formula. It really is just the Pythagorean theorem, but written for the coordinate plane, believe it or not. So that's kind of neat. All right, now I want you to take a look at this diagram that we have right here. First of all, do you remember from geometry what that thingy is? It's a Greek letter. What'd you say? No, good guess. Omega looks kind of like a...
I remember. It's like the...
Yeah, it's like a horseshoe with like the little tail sticking out. Now this one, and I draw mine a little bit different. I do it more kind of like an O with a loop-de-loop up on top, kind of. But that's just a Greek letter called theta. And it's not anything weird, or it's literally just a variable. It's just like using x, but we usually use it in reference to an angle. That's all. So that's just me saying this angle, I'm just calling it theta because I don't know what its measure is. That's all, okay? So theta, that's the name of the letter, and it just is a variable for an angle. Let's stick that in there. Variable for an angle. For an angle. Okay, so what we're going to be doing is we're going to be taking different angles, putting them in standard position. So remember, that's when you have the vertex on the origin. One side of your angle is along the x-axis, the initial side, and then you have a terminal side that lands somewhere in one of the 4 quadrants, right? So I have this angle. What I'm going to be doing is I'm going to be taking that terminal side, wherever it lands, and I'm basically going to drop a vertical line to the x-axis to turn it into a triangle. So wherever it lands, it doesn't matter. So here I'm just going to drop a vertical line, and now I have this nice little right triangle. This, the hypotenuse, we're going to refer to as r. This distance, the horizontal distance, whatever it is going to be x, and my vertical distance is y. Okay, you with me so far? Everybody's all right? Okay, so now we've been talking about these trig functions over on the side here. We've been talking about sine, cosine, and tangent, You're doing a project on them already. So you already have some information about sine, cosine, tangent. Plus you use them in geometry, right? These ones down here might be new to you though. You may not have ever seen these before. Have you? Have you seen these? You have? Where'd you see them? Oh. So let's check out what they are. So sine, you're all familiar with sine. Sine, of course, is equal to what over what? If you remember the magic word? Opposite over hypotenuse. In fact, let's throw our magic word up here somewhere. How about maybe right up here? SOHCAHTOA. Just so we don't forget. So, opposite over hypotenuse. So if I take a look back at my... We're used to talking about the angle inside of the triangle, right? So normally I'd be referencing this angle. But it turns out since these two are supplementary, theta, this missing angle that I have, and this angle right here, they're supplementary, aren't they? So they actually can swap in and out for each other when I'm talking about the sine, cosine, and tangent of them. So even though this is my angle, it works the same as this guy. So what would the sine of this angle be? Wouldn't it be opposite, which is y, over hypotenuse, which is r, right? Right? So that's exactly what I'm going to have here. So my opposite side is y over my hypotenuse r. Okay, cosine is adjacent over hypotenuse, right? Adjacent hypotenuse. So for us, that's now going to be x over r, right? According to this diagram, x over r. And tangent, as we know, is opposite over adjacent. So that will now be y over x. Okay, is everybody all right so far? All right. Now, a couple of things that I want to talk about. What are you never allowed to have in the denominator of a fraction? I think someone might have said it, but I'm not totally sure. I was going to assume that someone said 0. You're not allowed to have 0 in the denominator, right? That breaks everything. If r were 0, so the length of that hypotenuse were 0, would I even have an angle? No, I wouldn't even have an angle. So I really don't have to worry about a scenario where r is 0, because then I don't even have an angle. But could you imagine an angle where x was equal to 0? Think about, I wish that at this terminal side here, imagine it as a thing that can move around, right? The initial side stays here, but then that terminal side can really go wherever I want to put it. Could you imagine a location where this terminal side could land so that x would be 0? Remember what x is? It's this distance. Could it ever be 0? Yes. What if this terminal side, instead of being over here, what if it was on the y-axis? Then I wouldn't have a horizontal distance at all. Because remember how we created this triangle? I took a point on my on r, and I dropped a vertical line to the x-axis. If r is here, and I drop a vertical line to the x-axis, this is my angle, right? But I don't have a horizontal distance. So x could be 0. That is possible. For the same reason y could be 0, right? Because what if that terminal side was along the x-axis? So now I have no height, right? Because it's just flat. So it is possible that I do have a value for r, but x or y could potentially be 0. So why is all that important? Because of tangent. We just need to make a note that because I'm never allowed to have 0 in my denominator, I have to specify that I can't have an x value that's 0. Otherwise, I'm going to end up with a 0 in my denominator. So let's just make sure that we note x cannot equal 0. Y can, but x can't. All right. These next 3 are very closely tied with the 3 above them. Do you remember how they're related? Oh. Do you know what the name of this one is? CSE? Yes! This thing, if you say it out loud, is called cosecant. Cosecant. This thing, SEC, that's just secant. And cot, C-O-T, that is cotangent. So, what in the world are these things? Well, it's actually kind of cool. They are basically the reciprocal of the one that's right above it. So, cosecant is actually equal to 1 over sine, which is really just its reciprocal. So, I would have r over y. Similarly, secant would be 1 over cosine, or r over x. And cotangent, I just flip the tangent over, x over y. Now, I do need to worry about my denominators because remember, r can't be 0, otherwise I don't have an angle. But I can have x's and y's that are zeros. So I do just need to say, all right, here, y can't be 0. X can't be 0 here, and I can't have a y be 0 in that one. Let me zoom out a little bit. Okay, so this has been a lot of information. Let's sort of try and work our way through a problem and see how we apply all this. All right, so A says the terminal side of angle theta in standard position passes through the point 12,5. Find the value of all 6 trig functions for angle theta. All right, so here's what we're going to do. First of all, I'm going to just sketch myself an x and a y. And then I'm going to plot approximately where the point 12,5 would be. So 12,5 is probably somewhere about there. Okay, you with me so far? Everybody's good? Yeah? All right. So let's reread. The terminal side of an angle theta in standard position. So that means I have an angle. One side is along the x-axis. And then the other side, the terminal side, they're saying goes through this point. So that's my angle. That's my angle theta that they are talking about. I'm supposed to find the value of all 6 trig functions for this angle. Now, remember what we did in our example over here. I took a point on R and I dropped a perpendicular to the x-axis. I'm going to do the exact same thing. I'm going to drop it from the point that they gave me. Drop myself a perpendicular, so I have now created for myself a right triangle. And I know a whole bunch about this right triangle, believe it or not. Don't I know what this value is? What is it? What'd you say? Oh, that angle's 90, but this distance, you know it. You know how long this side of the triangle is. It's got to be 12. If that point right there is at 12, 5, that means this is 12 and this is 5, doesn't it? Do you guys see that? So that's 12 and that's 5. Does that make sense? Okay. Now, if I look at the 6 trig functions, so now I have the y, I have the x, and I'm going to need the r. Well, lucky for me, can I find the hypotenuse of a right triangle if I have the two other sides? Yes, I can. You might already know it if you remember from geometry. Anybody know what the hypotenuse is going to be without even doing the math? You just know it? Anybody know it? No? Okay, so let's say you don't know it. How would we find it? Pythagorean theorem. A squared plus b squared equals c squared. So let's pop those pieces in. 12 squared, 5 squared. Always make sure that c is the hypotenuse, right? A and b don't matter. You can mix those up. But c has to be the hypotenuse. So that's 144 plus 25. That's 169 equals c squared. So the square root is 13. I was hoping someone would have remembered that Pythagorean triple. I don't know if you remember learning about those, but that's when you have a right triangle and all three sides are whole numbers. Do you remember the 3, 4, 5 triangle? Yes, I hope so. So a 3, 4, 5 triangle is another one of those Pythagorean triples. 3 squared plus 4 squared does equal 25 squared. And that's a great one to know because first of all, it's easy. It's 3, 4, 5. But all of its multiples are also Pythagorean triples. So 30, 40, 50. Or 9, 12, 15. If you just take them all and multiply them by 3 or whatever. So it can save you a lot of time. You don't actually have to do the math out if you happen to notice a Pythagorean triple. All right, any hoosers, I have the 3 sides of my triangle, so now I can give all 6 trig functions. So check this out. Sine, look right back up here. Sine is going to be y over r. So what is that in my case? What's y over r? Someone's saying something. Yes, 5 over 13 is correct. Y is my vertical distance. X is always my horizontal distance. And then R would be my hypotenuse. So if it's y over r, yep, 5 over 13. Cosine, that's supposed to be x over r, so that would just be 12 over 13. Tangent, that's y over x, so that is 5 over 12. Cosecant, I don't even really have to look up at my list. If I know that it's just the reciprocal of sine, isn't it just 13/5? I don't even really have to do the workout. Secant would just be 13 over 12. And cotangent, 12 over 5. I also have good news for you. Probably tomorrow, I'll be giving you the reference sheet that you can use on everything. These are all on that reference sheet, so you don't have to memorize any of this. Okay, so we got through A. Was that good? We can handle that? Alrighty. Let's check out B. The terminal side of angle theta in standard position passes through the point 8, -6. Alright, well, I'm going to do the same thing. It's just that now I have, let's see, 8, -6. Be about there. So I still have my initial side is along the x-axis. The terminal side now is right there. Okay, so I'm going to drop a perpendicular to the x-axis. So this time it's going this way. Okay, you with me so far? What is my horizontal distance? 8. Now, here's where things get a little weird, okay? It's a little weird here because this refers to my vertical distance and I'm down 6. And I know in geometry you never deal with a negative side of a triangle, but you have it here because I'm going to call this side -6. I know it feels weird because it's like, well, it's a triangle. How could I have a negative side? But it can on the coordinate plane, right? Because I'm dropping down 6 units. The cool thing is that R, no matter where R is the length of the hypotenuse. It's not a distance that I've gone left, right, up, or down. That's what X's and Y's are. R is just what is the measure of this length right here. So R will always have a positive value. Think about it. If I do a squared plus b squared equals c squared, it doesn't matter if a or b are negative because I'm going to square them anyway. Does that kind of make sense? So if you remember what I just said about a 3, 4, 5 triangle, and this is a 6, 8, you already know what this side is. 10, it's got to be a 10. And if you don't know it, you can just do Pythagorean theorem. And you'll get it. But I'm telling you, you want to recognize 3, 4, 5 triangles. Because they come up all over the place and it just saves you so much time. All right, so let's talk about this. So here's my angle. There's theta right in there. And I want my 6 functions again. So sine is going to be y over r. So what's that? -6 over 10. Now, I can reduce that, so I should.
Cam, what was that?
All right, there's sine. Let's do cosine. Cosine is x over r, so that's just 8 over 10, reduces down to be 4/5. And tangent, y over x, -6 over 8, or -3/4. And then again, to get the next 3, I don't have to do any more math. I'm just going to take the reciprocal of everything above it. So cosecant is now going to be -5/3. Secant is now 5/4. And cotangent is now -4/3. Okay, so far so good? We're getting there. We're almost done. This next one's a little weird, but it's not that bad once you figure out what you're doing here. Alright, so we can find the 6 trig functions using any point other than the origin on the terminal side of an angle. Yep, we talked about that. We can also find the 6 trig function values of an angle if we know the equation of the line coinciding with the terminal angle. So this next problem, instead of them just telling me that the terminal side runs through this point, they're giving me the equation of a line that overlaps the terminal side. All right, so let's try this. Here's what I would do. I would, first of all, figure out what the slope of this line is. So I wish I had more room. I'm going to try and squeeze it in here. So first, let's find the slope. Find slope of that guy. Do you remember how to find slope? If they give me the equation. So I'm sure you all remember y equals mx plus b, right? This is not in that form though. So you have two options. You can either rewrite it so it looks like y equals mx plus b, or if you remember that that's standard form and you can get the slope by doing negative a over b, then you pretty much already have it. But I have a feeling that most of you are going to forget that part. So why don't we 3x minus 2y equals 0. If I want to find the slope, let's get it in y equals mx plus b form. I get that the slope is 3/2. Did you get that? Does that make sense? Are we okay so far? Have I done anything too crazy? All right. So now I'm going to draw my little picture of what is even going on. Okay? So I have an x and y axis. I have an angle in standard position. So I know the initial side's right there. They're saying that the terminal side and this line like overlap each other. So if I just draw this line, I know my terminal side is under there. So y equals 3/2 x. Well, wouldn't you just start at the origin and then go up 3 over 2? Right? And you could keep doing that. You can go up 3 over 2, up 3 over 2, up 3 over 2. But let's go up 3 over 2, and there's another point on my line. So that was up 3, here's 2. Now, it doesn't matter what point you pick on your terminal side to turn into your triangle. You can pick any point that you want, so I might as well pick that one. If I go up 3 over 2 and I drop this perpendicular, look what I know. I know this is 2, and I know this vertical distance is 3. Does that make sense? Do you all see how I got there? Okay. Great, now I have x and y, all I need is r, and then I can do the ratios just fine. So we just have to find r. Unfortunately, this is not a Pythagorean triple, so I'm going to have to do it out. So a squared plus b squared equals c squared. So 4 plus 9 looks like I get the square root of 13. Does that make sense? Everybody's all right? Okay. I know I asked that a lot, but stop me if you don't know what I'm talking about. And now I have all the pieces that I need to find the 6 trig functions, right? So let's see if I can squeeze them in here. Sine, remember, is going to be y over r, so that should be 3 over root 13. But, of course, we have to make things difficult in math. Are you allowed to leave a square root in the denominator? No! You have to fix that. Do you remember how? Yeah, do you remember how to do it, though? Yes, you multiply by root 13 over root 13. So you actually get 3 root 13 over 13. Annoying, but doable. So now I'm really going to run out of room. Cosine that's going to be 2 over root 13. And then I have to fix that. So that turns into 2 root 13 over 13. Tangent 3 over 2. That one's easy. Cosecant, remember I want the reciprocal of sine, but let me give you a little insider's tip. if you look at sine, if I take my final answer and take the reciprocal, you have a square root in the denominator again. And that's annoying. Go back to the one before. If you take the reciprocal of that, you don't have a square root in the denominator anymore. So it's just root 13 over 3. So it's always worth writing it down. So that's cosecant. Now we need secant would be, same thing's going to happen, right? I don't take my final one. I took the one before it, root 13 over 2. And cotangent. That one's just 2/3. Woo! Okay. There is a little bit more of 1-3, but I think we'll save that for tomorrow.